Recall from Module 5.2 that the walled method is not the only, and indeed it isn't even the best way to approach inference for GLMs. The walled approach is based on an approximation to the likelihood at beta hat, and it does not necessarily provide accurate information about values of beta far from beta hat. Here we will discuss an alternative approach to testing and constructing confidence intervals based on likelihood ratios and see that it suffers less from the approximation problem. So thus far we have been basing all of our inferences on this result right here. And so essentially, remember what this result does is it gives us an approximate distribution for our estimator. So here we've got beta hat is approximately normal, where that distribution is centered at beta. And then here we have the variance term. And notice that the variance term does contain that weight matrix that we've seen previously. So the walled approach has the great advantage of simplicity. Basically all you need to know is the estimate beta hat and its variance. And it's possible to construct by hand all the test and confidence intervals you need for any element of beta or any linear combination of the elements of beta. So these are called walled test or walled confidence intervals, etc. Recall, however, that this result is based on an approximation to the likelihood at the MLE, and the approximation may be poor at values far away from beta hat. So now let's consider likelihood ratios. So a competing approach is based on likelihood ratios. So we consider the univariate case first, comparing a likelihood and an arbitrary value of theta with the MLE theta hat. And so here we could construct a lambda equal to the likelihood evaluated at theta over the likelihood evaluated at theta hat. And then it ends up, if your sample size as it approaches infinity with IID theta subject to regularity conditions, it ends up that you can show if you take minus 2 times the log of lambda, that's going to converge in distribution to a chi-squared distribution with degrees of freedom 1. And so you may ask, well, why are we taking negative 2 log lambda? This idea actually goes all the way back to BST 675. So remember in BST 675, we might have a value that we're interested in its distribution, but that value doesn't have, a nice known distribution. So often what we'll do is we will take functions of that value we're interested in, and sometimes those functions will have nice distributions. So that's exactly what's going on here. So lambda by itself doesn't have a nice known distribution, so that's why instead we're going to work with minus 2 log lambda, because it does have a nice distribution. And so this result can be extended to multivariate and non-IID cases as well. So for example, consider 2 models. So we're going to have a full model and a reduced model. So a couple things just to note on notation here. So the first one is, notice that we have beta superscript 1. This is really the same thing as beta subscript 1, but the reason that we're going to use the superscript here is because we're going to set some of these be equal to a constant, and the ones that are equal to a constant, we're going to denote that with a 0 subscript. So instead of having 2 sets of subscripts, because usually if you have 2 sets, that denotes like a column and a row, that's why we're using the superscript here in this notation. All right, so the full model in this case is going to partition beta, which is a vector of our parameters, into beta 1 and beta 2. So here we're going to partition the vectors into 2 parts. The full model is going to have both the first part and the second part. Now, just like I said over here on the right-hand side, you could just as easily think of that first part as being beta 1 and beta 2. Now, one thing that this notation does do for us is it gives us a little bit more flexibility, so we could think of it as that simple case. We could also think of a model that maybe has beta 1, beta 2, beta 3, beta 4, and maybe we want the first 2 to be comprised in beta 1 and the second 2 to comprise beta 2. So the superscript also provides us a little bit of flexibility here. All right, now in the reduced model, the first part of the partition is going to be set to a constant. And so here we're denoting that by adding in that subscript 0. Now most of the time we're going to set those constraints to be 0 in the hypothesis test. So for example, what we would be doing in this particular case, since we're going to set all the parameters in beta 1 to be equal to 0. In other words, what we would be testing under the null hypothesis if we were using this is that beta 1 is equal to beta 1 naught, where beta 1 naught are constant, so these could be equal to 0. 0 is the most common one because when we think of hypothesis test for our coefficients, we usually see beta equal to 0. Now, of course, we don't have to use 0. We could use whatever we want. It's just 0 is the one that usually makes the most sense. All right, so just kind of a quick note here. So if you'll recall, in BST 681, we looked at the nested f-test, and the nested f-test also used this idea of a full and a reduced model. And so it ends up that for ordinary least squares, what we used, in linear regression, that f-test is actually equivalent to this likelihood ratio test. So you can show that the two are equivalent. All right. So here, again, we're going to let lambda denote the likelihood ratio comparing the reduced to the full model, and then the value that we're actually going to look at is minus 2 log lambda, and again, that's because you can show that this has a nice distribution, and it's approximately distributed chi-squared 1. Chi-squared q, where q is the length of beta 1, and typically the number of parameters assumed to be 0. So notice, back on the previous page, we had chi-squared 1, but the reason for that is we were first looking at the univariate case. So when we're in the multivariate case, that 1 becomes q, where q is the length of beta 1. So in other words, the is the number of parameters that we're going to set equal to a constant, or usually we set those equal to 0. And so this result allows us to carry out a hypothesis test by calculating the following. So since we know that minus 2 log lambda follows a chi-squared q distribution, we can find p-values by comparing the test statistic resulting from a negative 2 log lambda to a chi-squared distribution. So in a picture here, I do have a chi-squared distribution with q degrees of freedom. So if we think of in terms of our p-value, really what we're doing here is we're looking at the area to the right of that endpoint negative 2 log lambda. So just like we have found pretty much every other p-value you've ever looked at. It also allows us to construct 1 minus alpha confidence intervals by inverting the above test. In other words, find the set of parameter values such that those values would be less than or equal to that endpoint that has 0.05 to the right if you're looking at 95% confidence interval, 0.1 to the right if you're looking at 90% confidence interval. All right, so just kind of looking at this ratio, let's talk a little bit more about this ratio and why that ratio of likelihoods helps us. So let's say that beta 1 really is 0. And remember again, so beta 1 could represent multiple parameters, and we're saying that all of those are equal to 0. So if that is the case, if we look at this likelihood piece right here, notice, and I'm just going to kind of shorthand write it this way, but we're talking about that likelihood ratio. Notice that this is really going to be approximately 1, because, if that reduced piece truly is 0, you're pretty much going to have the same likelihood in the top and the bottom. And then from there, notice that minus 2 times the log of 1, well, log of 1 is 0, so that's going to be equal to 0. And so then if we think of what a chi-square distribution looks like, remember that a chi-square distribution's lower bound is 0. So what that tells us is the area to the right of 0 has to be pretty much 1, since the total area under the curve is 1. So you would end up with a p-value of 1 in that case, which would mean you wouldn't reject. Those parameters really are probably equal to 0. So that kind of matches up with what we would expect to happen in comparing those likelihoods. So let's revisit that Donner Party example that we looked at in the last module. So what we want to do is we're going to compare estimating the effect of age on survival for females in the Donner Party and look at 95% confidence intervals obtained using both the Wald and likelihood ratio methods. So since we're interested in estimating the effect of age on survival for females, what we're really interested in here is the interaction term. So if we think of the full model is going to contain 3 coefficients, one for female, one for age, and one for the interaction term. And so the reduced model here would only contain female and age. So we can think of the parameter that we're going to set to a constant is going to be that interaction term, and we're going to think of it as being equal to 0 for our hypothesis test. All right, so here we have a plot here, and what we're looking at is we're going to compare the likelihood ratio in the walled as well as that chi-square distribution. So let's look at how we're going to do this. So first thing I want to focus on in this plot is I just want to look at this horizontal gray line right here. So what this gray line represents is the 95% quantile of a chi-square distribution with 1 degree of freedom. And notice we have just 1 degree of freedom here because we only have one parameter that we're setting equal to a constant. That is that interaction term. So if we think of a chi-square distribution and we want the 95% quantile, remember what we're doing is we're saying that 95% of the area is to the left of the point and 5% of the area is to the right. And then that end point that we're interested in is this end point right here. And so just as a reminder, in R, what you can use is the Q chi-square function. And here we want a 95% quantile with 1 degree of freedom. And you would find out in R this is approximately 3.841. And so notice that this horizontal line here is at negative 3.841. And you might say, well, why are we looking at the negative here? Well, if you'll notice here on the left-hand side, we have positive 2 log beta minus log beta hat. Whereas before, when we were up here looking at the test statistic, we had negative. So we have just flipped the signs there. So that's why you see that. All right, so now let's talk about the red curve. So in the red curve, you have minus log lambda for different values of the interaction term. So values extending lower than the gray line represent parameter values with negative log lambda lower than the chi-square. So therefore, the intersection of the red and the gray line define the likelihood ratio confidence intervals. And so we can see that where this red line crosses the quantile. Here and here. Now on the other hand, in the blue, we have what we would normally see for the walled interval for different potential values of the interaction term. And the reason we're going to work with this value squared instead of what you would typically see with the walled, in the walled we wouldn't typically see that squared, is because you can show that that follows a chi-squared, so it allows us to make this direct comparison. And so it ends up that the intersection of the blue and the gray line, this is where you get your walled intervals. Oops. So as you can see, the walled approach is incapable of capturing asymmetry like the likelihood function and must therefore always produce symmetric confidence intervals about the MLE. The likelihood ratio is not subject to this restriction. The downside, of course, is we must fit a new model at all of the different values for beta. So this impacts hypothesis testing as well. For testing the interaction term, the walled test gives a p-value of about 0.087, whereas the likelihood gives 0.048. Now for the Donner data, we only had 45 observations and we had p equals to 3, again because we had 3 different coefficients. So now let's compare what these approaches would look like if we had different sample sizes. So instead of 45 people, what would happen if we had less than 45 or more than 45? And what it ends up with, and here we'll just assume p equals 2 for simplicity for this illustration, but you would see similar things with p equal to other values. It ends up that the larger your sample size, the likelihood ratio and the walled intervals are going to agree with one another. The smaller your sample size, the less they are going to agree with one another. And so the walled approach enjoys popularity due to its simplicity. And it ends up that likelihood ratio intervals are, they're pretty difficult to construct by hand. The two approaches often agree quite well. However, there are also situations where they disagree dramatically, and in particular when you have small sample sizes. So test and confidence intervals based on log likelihood ratios are more accurate and should be trusted over the walled approach. All right, so here we're just going to talk about some common issues with logistic regression, and you saw these in some of the readings for the course. So just as in univariate statistics, when n is large, we can often ignore the fact that our data is discrete and just use normal approximations. However, when n is small, the problems can arise. And so consider the following data set. So here we're going to just have x, which is our single explanatory variable. Notice that it is continuous, and then y, our outcome, is going to be binary. So if we try to fit a logistic regression model to this data, we'll find that the algorithm will not converge, and we're going to get a warning message in SAS or in R. And the reason is that all of the events occur when x is positive and don't occur when x is negative. And so you can actually see that pretty easily if we just draw a line right here. Notice everything above the line has y equal to 0 and x negative, and everything below has y equal to 1 and x positive. So to put it another way, just like I said here, we can draw this line. And so this is what's referred to as complete separation, or more generally, you'll hear this referred to as monotone likelihood. And so here we have the likelihood evaluated at different values of beta. And so notice that it ends up in cases like this that the likelihood is monotone in beta, whereas previously, if we thought of, come back down here, what the likelihood would look like, it wouldn't have that monotonicity. So what it means is that the MLE occurs at infinity or negative infinity. Because again, there's no, curve here where your likelihood can be maximized. So this ends up having a number of ramifications. Your numerical algorithms are going to fail. All of your weights in your weight matrix are going to go to 0, and the standard errors are going to go to infinity. But the likelihood ratio tests are still going to be valid. This has a number of complicated ramifications for inference, which lie beyond the scope of this course. But practically speaking, the ramifications are that the data do not allow you to estimate a certain parameter in a way that the model is currently specified. And so this can occur when the models are over-parameterized, i.e. in models with many explanatory variables. Complete separation occurs whenever a linear predictor completely separates the outcome. In linear regression, estimates are only undefined if x is not full rank. In logistic regression, complete separation represents an additional restriction on the complexity of the design matrix. And then this last note here, fitted probabilities of 0 or 1. Finally, it is worth noting that you may sometimes see a warning along the lines of fitted probabilities numerically 0 or 1 occurred. And so this is very different from complete separation, because pi I is a function of e to the nu I. Extreme nu I values can easily produce fitted values with extremely close to 0 or 1. And so this causes problems numerically in the iterative least squares algorithm. And this occurs because wi is equal to pi I 1 minus pi I. So you can imagine, if pi I is close to 1 or 0 here, you're going to end up with 0. So keep in mind that this is a warning and not an error, and that the model can still be fit and all the usual inferential procedures applied. However, it is generally an indication that your data contain outliers, and some investigation into those with 0 or 1 probabilities is typically warranted. And then finally, down here at the bottom, I do have how in both R and in SAS to construct those confidence intervals for both the walled and the likelihood ratio.